We always talk about the moon as like Earth's only natural satellite, right?
Right.
But what if I told you there might be something else up there?
Hmm.
Something a lot harder to see. Today, we're going deep on the story of Earth's dusty pseudo-satellites.
Yeah, we're talking about the Kordylewski Clouds, or KDCs for short. They're these super faint, like really faint dust clouds hanging out near these points called L4 and L5.
Okay.
They're these kind of gravitationally interesting points.
Ah.
They trail and follow the moon in its orbit. They're named after this Polish astronomer, Kazimierz Kordylewski, who first suggested they might exist back in 1961.
And suggested is the key word there, right?
Yeah.
Because actually seeing these things,
Yeah.
it's been like trying to take a picture of a shadow.
It's really hard. It's a huge observational challenge.
For years, it's been a real mystery for scientists.
Totally. Imagine trying to see this, like, whisper of dust against the blackness of space. Lots of people wondered if what people saw before were just like tricks of the light or problems with the instruments.
Yeah, and that's where this really cool new research comes in, right?
Exactly.
A team in Hungary, led by Gabo Horvath, has published some pretty convincing new evidence. It really makes you believe these dusty companions are actually out there. Their work was published in the monthly notices of the Royal Astronomical Society, by the way. So what did they do differently? What let them see something that others couldn't confirm before?
Well, they had a clever approach.
Yeah.
They look at how light acts when it bounces off little particles like dust. Okay, so these L4 and L5 points,
Yeah.
the Lagrange points we talked about.
Yeah.
Imagine the Earth and the Moon making 2 points of a triangle, and those Lagrange points are the third point, either ahead of or behind the Moon. They're special spots.
Okay.
The gravitational forces of the Earth and the Moon and the Sun, too, a little bit, they all kind of balance out there. So it creates these almost like parking spots, semi-stable parking spots for interplanetary dust, the tiny grains floating around our solar system.
Semi-stable. That's an important difference, isn't it?
Right.
It's not like they're totally stuck there forever.
Think of it like a slow swirl in a river. Stuff can get caught there for a bit, but it might not stay forever.
Oh, okay.
The sun's gravity is pulling on everything, so the Lagrange points are more like temporary hangout spots.
Okay.
This Hungarian team, they use polarizing filters.
Like the ones that cut glare from water?
Exactly.
Okay.
They used them to look for sunlight that bounced off dust at the L5 Lagrange point.
So they weren't just looking for any faint light. They were looking for light that had a specific orientation after it bounced off the dust.
Yeah, you got it. When light waves hit dust and scatter, they often get polarized. It means their waves are vibrating more in one direction. The amount and direction of this polarization can tell us a lot about the dust itself and how the light was scattered.
Okay.
What they saw was a specific pattern of polarized light, and it matched their earlier predictions and what other people had seen in those debated historical observations.
Huh.
That's a strong sign they were seeing light scattered by a real dust cloud, not just some weird optical illusion.
Wow, that's amazing.
Yeah.
It's like finding a faint echo of dust in all that emptiness.
It is.
And the research paper even has a quote from Judith Slisbelow. She calls the KDCs two of the toughest objects to find. It really shows how hard this was and how important this discovery is. I mean, the idea that Earth has these dusty companions along with the moon is mind-blowing.
It really is, like finding a secret room in your house you thought you knew everything about.
And this brings up something interesting. The research talks about what could we do with these Lagrange points in the future. It could be the KDCs themselves, too, like using them as places for space probes to orbit, transfer stations for missions going further out, and this one's kind of wild, maybe storing pollutants there.
Yeah, that last one is interesting, but we need to be super careful.
Right.
We don't fully understand how stable those dust clouds are in the long term. And we have to figure out if the dust itself is dangerous to spacecraft or future human missions. We don't want a dust cloud messing up sensitive equipment.
No, definitely not. But thinking about it, the idea of using those Lagrange points as like stepping stones for space travel seems really important.
For sure. Because of the way gravity works there, it takes less energy to keep a spacecraft around a Lagrange point, compared to staying in orbit around Earth. They'd be great for refueling stations, places to build big spacecraft, or even bases for science further away from Earth.
So they're not just dust clouds, they could be like cosmic crossroads.
Exactly. They can make deep space missions cheaper and easier, like pit stops along the way. Imagine a spacecraft going to Mars, stopping at L4 or L5 to get more fuel or new parts.
That's pretty cool.
It is.
Makes me think, what is this dust actually made of? If we might use these places, we need to know what the KDCs are made of.
That's a fundamental question. Dust is everywhere in the universe. It's what stars and planets form from. In our solar system, most of the dust comes from the protoplanetary disk, the cloud of gas and dust that was around our sun when it was young. It also comes from asteroids and comets smashing into each other and making little pieces. And a teeny bit is interstellar dust, stuff that's traveled from other stars.
Wow. So the Kordylewski clouds could be like a cosmic mix of dust from all these different places.
You could say that, yeah.
Yeah.
And what's cool is that the dust in the KDCs might be really pure. There's this idea of an energy barrier around them. It might protect them from dust from Earth or our stuff in space. That means the dust there might be more like how it was when the solar system was young, or even from interstellar space.
So studying it would be like looking at a time capsule from when our little corner of space was born.
Exactly. It would teach us about those early days and maybe even about stuff from outside our solar system.
The paper says it might not be that hard to get to the KDCs, maybe 100 days with low energy orbits. That's pretty quick, space-wise.
Oh yeah, definitely. Compared to years to get to the outer planets,
Yeah.
100 days is pretty quick.
The idea of dust collecting at Lagrange points, that came from somewhere, right?
Oh yeah, it wasn't just a random guess.
Yeah.
They found Trojan asteroids at Jupiter's Lagrange points.
Right.
The Trojans are big groups of asteroids sharing Jupiter's orbit, going ahead and behind it. They were the first proof that these gravitationally balanced points could trap stuff. So it made sense to ask, could that happen with dust in the Earth-Moon system too, even if it's much smaller?
Okay, so we kind of get where these clouds are and why dust gathers there.
Right.
But how do they actually work? The dynamics of these wispy clouds, that sounds super complicated.
It is super complex. The best models we have now say the KDCs probably form from interplanetary dust,
Okay.
and they get caught temporarily by the gravity of the sun, earth, and moon all pulling on them. It's this delicate dance, and those clouds aren't just sitting there.
Yeah.
They're changing all the time. Their density and structure shifting. That's a big reason why they've been so hard to see consistently.
It's like trying to map a weather system that never stops changing.
Exactly. And it's not just gravity.
Oh, right.
There's the sun's radiation pressure. That's the actual pressure from sunlight pushing on the dust particles. The solar wind, too. That's a stream of charged particles from the sun. And then there's this thing called Poynting-Robertson drag. It makes dust particles slowly lose energy and spiral in towards the sun.
Wow, so many forces at play.
Yeah.
But even with all that, dust can still stay around the Lagrange points for a while.
Yes, if they're in the right kind of orbit around the Lagrange point, they can hang out there for a good while.
I remember reading that the dust can become electrically charged, too.
You're right.
Doesn't that add even more complexity because of the magnetic fields around Earth and the moon?
Absolutely. Dust particles in space, they often get charged up from interacting with sunlight and the stuff floating around out there. These charged particles are then affected by the magnetic fields around Earth and the moon, so their paths get even more complicated. Could be why the KDCs are so intricate and dynamic. It's a tough system to model perfectly.
This all has a pretty long history of people trying to observe them. You mentioned Kordylewski's work, but there were others, right?
Yes, after Kordylewski's photographs, other researchers like Simpson and Roach said they saw them using different methods. Later, Winiarski took pictures that seemed to show the clouds too. But because it was so hard to see them again and they were so faint, a lot of scientists weren't sure if they were really stable or even if they were really there at all. Some thought the sun's gravity would just scatter any dust pretty quickly.
It sounds like a real scientific mystery.
Yeah.
But the work by Slisbelow and her team in 2017, using that polarized light photography from the ground, that seems to have made the evidence a lot stronger.
It's
They
evident.
actually saw something.
Exactly. What they did from the ground, those observations really helped. It backed up the idea that there really is dust collecting at the L5 point, even if it's always changing. By carefully measuring how the light was polarized, they could tell a dust cloud was there and even figure out some of its properties.
From what we've learned from the ground, do we have any idea about what the KDCs are like?
Yeah, we have some rough ideas, like how dense they might be and how big they look in the sky.
Okay.
Current guesses say that if the KDCs are a distinct clump of dust, there might be something like 100 particles per square centimeter. But if they're not a big clump, just regular interplanetary dust in that area, it might be more like 5 to 30 particles per square centimeter. For their apparent size from Earth, they think they might cover about 6 degrees. It's actually huge, like 12 times bigger than the full moon. But they're so dim, probably less than 1 magnitude fainter than the sky around them, which is why they're so hard to see.
Less than 1 magnitude.
Yeah.
That's incredible.
yeah.
It really shows you how hard it is to see them. It's like trying to spot a slightly dimmer star right next to a really bright one.
It is.
It makes you think, why not just go there? Go directly to them from space. The paper mentions that people have been suggesting missions like that since 1963 by a guy named Cleor.
Yeah, scientists have wanted to send a spacecraft to those Lagrange points for a long time to actually get samples of the dust and study it. There are two main ideas. One is a flyby mission, where a spacecraft just passes through quickly and takes measurements.
Okay.
And the other is a rendezvous mission, where a spacecraft orbits a Lagrange point for a longer time to get more detailed observations.
Didn't the Japanese Haiten mission try that?
They did.
I thought they didn't find much dust.
They didn't find a lot, but that doesn't mean the KDCs aren't there. The Haiten mission only made very short visits to L4 and L5, like a single loop around each. Because the KDCs are so changeable and might be patchy, it's possible they missed the denser parts. Plus, the spacecraft was moving pretty slowly compared to the dust, which could have made it harder for their instruments to see it.
So what's the best way to study these clouds in the future?
Yeah.
The paper talks about a plan with both observations from the ground and missions from space, with some specific goals for both science and engineering.
That combined approach seems like the way to go. For science, we want to know exactly where the KDCs are, how stable they are over time, and how dense they are. And we need to directly measure the dust particles, things like their charge, mass, and how many there are. And like we talked about, figuring out what the dust is made of is super important to understand where it comes from and how it's changed. For engineering, these missions will help us figure out how to operate in the space between Earth and the Moon, test how to get to and stay around the Lagrange points, and build better dust detectors that can work with different dust speeds.
The space part of the plan sounds pretty complicated. It mentions going from Earth to the Moon, flying by L4 and L5, using the Moon's gravity to get to a Lagrange point. They mention L4 as an example.
Right.
And then staying in a patrol orbit for a long time, maybe more than 3 years, all with a special dust detector on board.
Yeah, that's the idea.
Okay.
By staying there for so long, the spacecraft could really study the dust environment over time. It might be able to see denser parts of the KDCs and learn how they change. And that dust detector would be designed to measure a wide range of dust speeds, fixing some of the problems with past missions.
Let's talk more about the ground-based part. It says they'll use extinction, scattered radiation, and polarization. What's extinction?
Extinction is basically how the dust clouds might block or scatter light from stars behind them. Astronomers can look at the light from those stars and see if it changes, like if it gets dimmer or its color changes as it passes through a KDC. That can tell them about the size and shape of the dust particles. And by comparing those changes to what we see with interstellar dust, we might even figure out where the KDC dust came from.
So it's like using the KDCs as a giant lens to study stuff that's even farther away.
Kind of, yeah.
What about scattered radiation?
That's just the sunlight bouncing off the dust in the KDCs. By looking at how bright it is and what colors it's made of, scientists can learn more about the size and makeup of the dust grains. But it's super faint, so it takes really dark skies and sensitive instruments to see it. And the clouds changing shape as the moon goes around Earth makes it even harder.
Right, like that shifting fog analogy, and then there's polarization. We talked about how the Hungarian team used that. How does studying polarization help us understand the KDCs more?
Well, like we said, sunlight gets polarized when it bounces off dust.
Mm.
And how much it's polarized depends on things like the angle and what the dust particles are like. Now, the angle between us, the sun, and the KDC, that changes as the moon orbits Earth. That means the polarization of the light from the KDCs should change in a predictable way, too.
Okay.
That changing polarization is a good way to tell the faint light from the KDCs apart from other faint light in the sky, like zodiacal light and counterglow, which have pretty steady polarization. By carefully tracking those changes, we can learn more about how the dust is spread out and what it's like in the Kordylewski clouds.
So it's like using 3 different ways of looking at life, how it's blocked, how it's reflected, and how its waves are arranged to understand these incredibly faint clouds.
You got it. Each method gives us a different piece of the puzzle. And when we put those together with what we learned from space missions, we have the best chance to finally solve the mystery of the Kordylewski clouds.
It's amazing to think about these elusive clouds, these maybe companions of Earth. Thanks to a lot of research and some clever techniques, it seems like they're becoming more and more real.
They are. And as we've talked about, these dusty pseudo-satellites give us a special chance to study cosmic dust that hasn't been changed much. It's a window into the early solar system and maybe even stuff from beyond. It's a huge opportunity for science.
And all the work being done and the missions people are proposing to study these clouds from Earth and from space, it's all super exciting. It feels like we're about to learn so much more about our corner of space.
I agree. And we shouldn't forget that those Lagrange points, where the KDCs are, could be really useful for space travel in the future, maybe even for other things we do in space. But we have to understand that environment first, including any dangers from the dust, before we do anything else there.
It makes you wonder, doesn't it? They're in such unique places, and with so many tiny particles, what other strange and unexpected things might be hidden in those clouds, just waiting for us to find them? It gives you a whole new perspective on how complex and mysterious space is, even right here near us. Thanks for going on this deep dive with us today.
It was my pleasure.